So today we start with a new lecture, new lectures in general, I would say. There is a change. So we have now Davide Pagani from Bologna, who's telling us about the challenges of the standard model and in quantum field theory. So he's telling us about after you realize the machine and the experiments, what do you do with the data? Do you have any theory for this data?
Yes,
Thank you.
So yes, today is the 4th day of the school, so you are already expert on the Muon Collider. But I was asked to speak about challenges of the standard model, quantum field theory at future colliders. It's a very ambitious title, I have to say. I will try to take this task, but I will focus in particular on the modeling of the hard production processes at future colliders, and the main focus will be the standard model case and obviously the muon collider. Okay, but in order to get to this point, I will also discuss proton-proton and E+E minus machine. Okay, so when I speak about proton-proton machine, I have in mind something like the LHC or the FCC HH, in which you have a collision at 14 or 100 TeV. And when I refer for E+E minus machine, for brevity, I always refer to the machine, let's say, at low energy, okay, in the sense that like at the order of 100 GeV, so the things that you have in mind like FCC, EE, or like CEPC, this other project. And obviously the main focus will be the muon collider, okay, the wonderful machine that we are speaking about in these days at 3 to 10 TeV, okay. But the interesting point is that in the past, we always had an alternation, okay, with these proton hadron colliders, plus minus machine. And you always, I mean, you can see these kind of collider like the precision colliders and these other colliders as the discovery colliders. So actually, the muon collider is combining some features that we'll see in the lectures of the two colliders. Okay, so it's both a precision and a discovery machine. But since it's a collider that is like a mixture of the two for some properties, it also combines the challenges of the two colliders. And I'm thinking about challenges in the description of the processes, so prediction from the theory point of view. Plus, it has something unique, okay? It's probing electroweak interaction at unprecedented energies. And as we will see, this is adding also additional challenges. So now I'm starting with just an overview, okay, of what we are going to discuss, and then I will go much more in detail. I was told that some of you are from accelerator physics, some of you are from phenomenology, so I'm starting from really basics and ending to more advanced topics, and I hope that in these 3 hours at least you can enjoy all of you can enjoy part of the lecture. So just to set the language, when we say discovery, what do we have in mind? Discovery, we have in mind really a collider, so like for example mu plus, mu minus, then something is happening in interaction here, and I'm producing a new particle, or similarly, a pair of like 2 new particles. Okay, so and important point obviously is that if you have to produce these 2 new particles, for example, the square root of s of the collider must be larger of 2 times the mass of the particle that you produced, like O1, just 1 in this case. And obviously when you say you produce this particle, you could in addition have also other one that are emitted at the same time. So the particular things of the muon collider, and this was already introduced also by Hitoshi yesterday, is that as we will see, it can be seen also like a vector-vector collider. Okay, so in fact you are probing interaction that are of this kind, processes, like in which this one is one of the electroweak electroweak boson. And although E plus E minus colliders are also colliding leptons, at this energy, this picture is not true, okay? Mostly you can think about the E plus E minus collider just as colliding two elementary particles. And these other vector boson-induced processes are practically negligible, okay? So we have a collider that is probing high energies. It can probe different kind of interaction, okay? And when I say instead precision, what do I mean? Precision is I'm measuring some processes from the standard model and I want to measure it precisely. So an example, I can have the production of TT bar that can happen in a different way. This is always smooth plus, smooth minus, neutrino, neutrino, W, W, T, T. Okay, and as you see, I'm drawing the TT bar production of two top quarks. Since during the lecture I'm switching from one collider to another, one properties to another, I'm not also changing the processes all the time. So I'm trying to use always as a reference this process. Why? Because it's an heavy object, it's interacting electroweakly, also in QCD. So we can see how it's different, for example, the modeling of this process itself, and you can then extrapolate for many other cases, many other processes. And but obviously, this is not the only process you can study at a muon collider. And something I want to stress is that precision per se is not a value from a fundamental point of view. So the fact that you know some parameter from the standard model with 1 or 2 digits more, you're not learning really something something more. So I mean, the value of this is another thing. So it's true that we are physicists. Sometimes we are picky, especially people like me doing precision physics who want to have everything in order. But the value of this is something different, and it's precisely what was mentioning yesterday Hitoshi. So that we have a theory, okay, that is working perfectly at Collider, okay, that is the standard model, but it's not true when you look, for example, outside to collider physics, from dark matter problem, dark energy, or antimatter matter symmetry, and this is very incredible because if you think about it, the standard model is just 18, let's say plus 1 parameter, okay, because you have 9 fermion masses, or alternatively the Yukawa, then the CKM that is giving you 3 angles, and 1 phase. Then you have the mass of the X, or alternatively lambda of the potential. Then you have GS or alpha S, the strong coupling, and especially you have 3 electroweak parameters that can be alpha, MZ, MW, but this is just a set. You can also decide to use another set like alpha, the Fermi interaction, MW. So you have 18 parameters plus 1. What is this plus 1? Well, this is actually a term that I don't want to dig into it, but it's the strong strong CP term, okay, the one that is related to the CP violation in strong sector, that in principle you could write in the Lagrangian standard model, and but it appears to be 0, or at least very constrained from measurements, and this arises all the problem of strong CP problem, the axion. These are like 18 parameters, and you have like infinite prediction that you can do. Any kind of process you have in the past decades of the collider, they are practically described in a very good way. There has been tension that appeared and then disappeared. But the problem is that nowadays we know that there must be beyond the standard model physics, okay, for the problem that I said before. For other theoretical problems, like the one that mentioned Hitoshi, like the hierarchy problems, and many others. but we don't have a clear indication of what is the new physics scale, okay? Okay, so how do we try to test then the physics of the collider? We want to stress test the standard model and see if there are if there are deviation. Because if there are deviation from the prediction standard model, this could be the sign of some new physics that is appeared there. So the typical picture that you see, for example, for the PP collider is exactly that you have, for example, an observables, like for example, the invariant mass of some objects in a process, sigma mxx, and your standard model prediction is this one. Maybe there is a resonance that is appearing at some scale. Okay, but could be that your collider energy is limited to this one. Okay, this is the square root of S of your collider. So you cannot see this peak, obviously, because it's beyond the energy of your collider. The best you can do is measuring the discrepancy between the standard model prediction and the prediction from the BSM. So how do you do that? Well, to do that, you need to have under control, obviously, the measurements at the desired precision. So this is like the BSM, and this is the standard model, and the reality is all together, but if you measure below this energy, you don't see the clear peak, okay? So to do that, you need two things, very good measurements, but also very good predictions, okay? So if you have an effect under like 1%, an effect here that is of the order of 1%, it means that your prediction of the standard model must be accurate at the percent level, because otherwise you can very easily misinterpret the deviation that you see in general as a BSM effect, also when it's not present. And this was there were cases in the past. And so when we will come back to this later, but when I refer to precise prediction, and you typically use a language that is the one of fixed order calculation, that you organize your computation in different order, number of loops. So you have typically, again, with the TT bar, the leading order, that is just these three level diagrams, the NLO correction, that are those involving one loop correction or one emission. And you have two kinds of them, the one of QCD involving strong interaction, and the one electroweak including electroweak interaction. So these are the dominant one, for example, in a proton-proton machine. Why? Because these are proportional to alpha strong, and you can imagine that alpha strong is of the order of 1/10, okay? While the one of electroweak correction are proportional to alpha, that is of the order 1/100, okay? 137, but let's say. So you expect that the electroweak correction are much, much smaller. And at LHC, for example, nowadays, these predictions are always at least accurate at NLO QCD. Otherwise, it would be really, you can very rarely fit the data with just leading order. And for some process now, even correction at higher level have to be taken into account. But in general, for LHC physics, besides some particular cases, NLO electroweak corrections are of the order of a few percent, because it's proportional to 1/100. Okay, so what we will see is that this will arrive at this point at the end of the 3 hours, but I want just to mention that the peculiarity of this collider is that, as I said, it combines the challenges of the two colliders, proton-proton, plus and minus, and additional one related to the fact that you probe the electroweak interaction at very high energy. Well, actually, what is happening is that when you calculate an NLO electroweak correction, these actually are not proportionally just to alpha, okay? But there are some contributions that are of weak origin, and so they are receive a correction of sin theta Weinberg squared, and this is like of the order 0.2, and especially some logs, okay, that go like the square of the energy of the collider over mw squared. Okay, so this is just an overview. We'll get to this in more detail. But it's saying something important. And this correction can be like not of the order 1, but can be of the order of 100%. Okay. So this is telling you that you build a new collider, you want to probe very high energies, okay, you want to probe the new physics at very high energy. You need to have under control your standard model prediction, and typically also at the percent level. And while you are doing that, some new effects from purely standard model physics is appearing, something that typically people never had to deal with in the case of LHC physics or E plus and minus. So you need also to have under control these effects, on top of all the other challenges that you always had at proton-proton collider and at the plus and minus collider. So besides the experimental challenge to build a collider, also the theoretical one to have under control the standard model prediction and so identify precisely the BSM are important. Okay. So, and before going to this point, let me try to remind you what is the structure of a prediction of a proton-proton collider, then a plus and minus collider, and see what we mean like the muon is a muon collider, a combination of the two. So now I have a bit of a overlap with also what Hitoshi said yesterday, but I hope maybe that listening to this the second time, you can understand it better. I can give some more details. And exactly this part of the lecture, if I have to give a title, okay, I would call it the hadronization of the lepton. So I'm not meaning to be clear from the beginning that there is some confinement or strong interaction. What I'm meaning is that when you go to a muon collider, you start with a collider that looks in a first sight like a plus and minus collider, and the more you go high with the energy, more and more starts to look like a proton-proton collider. Okay, but before going to that, I discussed before the proton-proton collider. Okay, so proton-proton collider, as we saw yesterday, if you want to calculate the cross-section for a process, production process of a final state F, you can write it in this way. So let me write it, and then I discuss what is each quantity. X1, F, F, J, E, X2, F, at P1, X2, P2, F. Okay, this is something that already Toshi discussed yesterday with some more details in. So you can write the hadronic cross-section split in two parts. The partonic cross-section, okay, so for example, in the case of the production of a TT bar, you can have in mind this process. Okay, I realize now that I forgot to show some slides about the past case in which the precision was not okay, but I can show you later if you are interested. And then you have, so this is the partonic cross-section, and then you have the parton distribution function. Okay, so this is like the probability to have the parton I that carries away a fraction x1 of the momenta of the proton. Okay, and this is similar the parton J from the other proton. And then the collision at the partonic level, as Hitoshi wrote, is happening not at S, the energy of the collider, but at S hat that is equal to S x1, x2. So the partonic process is really like at an energy that is much more reduced than the energy of the collider. Okay, and so there are these parts that are universal, so it's process independent, and it's something that you can, I mean, you can calculate with lattice QCD, but in practice, what is done nowadays is that you fit the prediction for some process to the data, and you extract the PDFs. And this other quantity instead is the calculation that you can perform with Feynman diagrams, is perturbative. So as you see, there is another quantity here that is this mu-f, okay? Mu-f is the factorization scale. Okay? So this expression here, if we are able to calculate it exactly, would be independent on mu-f, okay? This is not the reality because we cannot calculate it exactly. We can just calculate in perturbation theory. Okay, so mu-f is like taking into account, is like a technical scale that is separating the part of the of this prediction that you model within the proton and the part that you model in the process itself. And what is this this part that I'm referring to? Is the fact that, as also Hitoshi has discussed, the proton you can imagine as two U and a D that are going out, but actually every time you have a quark, okay, if you have a splitting with a gluon, this is a process that incredibly likely that it's going to happen. It is very much enhanced when the gluon and the quark are collinear, or the gluon is soft. Okay. And similarly, you can have the gluon that is splitting into gluon, same story, or having the gluon that is splitting into two quark, and again, this is enhanced when the two gluon are collinear. And you have to take into account this effect. Like, for example, if you want to model the TT bar production that we showed here, that we showed before, and this is quark. So you have to take into account that there are all these effects that are happening, and you can have multiple branches. You cannot just take into account one of the branching. And this is precisely what the Diglap equation are doing. So these are some equations that are taking into account all these emissions that are enhanced collinearly, and they are saying, okay, in this description, what do? I work in the collinear approximation, but you can imagine this scale, the physical meaning of this scale is like saying, like, okay, I have all this emission of parton that is collinear, but all of that in approximation that is collinear up to a PT that goes away from the beam pipe of the order of mu-f, I put it into the PDF and I resum all these branching that are incredibly large. Above this scale, instead, I leave it to the description of the cross-section. So in principle, if you could do this at all orders and this at all orders, moving the mu would lead you to the same prediction. In fact, we are not able, and so you typically use this you use the variation of the scale, for example, to estimate uncertainties. Okay, but as you can notice here, these are the PDF. It's just a plot of the same drawing that Hitoshi showed yesterday. Is that at low x, you see that the one that is dominating is the one of the gluon. Okay, so this is the green line that you see here. You see, you just move from the 1 and it's going very, very high up. So this is what also Hitoshi means, like a proton-proton collider are gluon-gluon collider, okay? And you can see it because this equation that I mentioned before, this DGLAP equation for the PDF, that are telling you if I increase the scale of some value of a bit, so I take into account more and more this collinear emission in the PDF, how the PDF is changing, and these differential equations are regulated by this Altarelli-Parisi kernel that you see here. And in particular, if you look at this GQ here that is telling you, if I start from a quark, what is the probability that I get emitting radiation, a gluon that is carrying a fraction z of the initial quark? This has a 1 over z. So this is incredibly announced for z that is going small. So this is telling you, look, it's very likely that you emit collinear photon when they are collinear gluon. When they are collinear, it's even more likely that you emit them that are soft. So practically, you're emitting a lot of gluon and a lot of gluon that are soft. Okay, and okay, we have this formula here that is written in this way, but I think that the best to understand the implication for the kind of distribution and the physics that you get at proton-proton collider is another one. So you rewrite this equation in terms of what is called luminosities, okay? Not the luminosity of the collider, but the luminosity, parton luminosity, these are called. So we said S is the collider, square root S, collider energy. Then square root S hat is the partonic energy. So S hat is equal x1, x2 times S. So now I change x1 and x2, for example, into tau and x1, in which I define tau as the ratio of S hat over S, that is equal to x1 times x2. So one can show that the same equation, I can rewrite it like sum over Ej integral tau min 1 in d tau sigma sigma hat I tau s l j tau u f, where l j tau u f squared is equal integral tau 1 dx x f x u f squared f j tau over x u f. So what is saying this equation? Rather than write it as two PDFs, I can directly introduce this object that is the luminosity. There is something related to the pair of partons that I choose. For example, if you take TT bar production, you can have at leading order the production of two tops via gluon-gluon or via quark-quark. Okay, so you will have the gluon-gluon luminosity or the quark-quark luminosity. Then you can decide if splitting in up-up, down-down, up-anti-up, down-anti-down. So it's saying, like, if I want to calculate this cross-section, I write it like the partonic cross-section at tau s, but tau s is just, you see, S hat, okay? times a luminosity. So it's like, now you can interpret this like the probability inside the collider to get a luminosity of a given tau, okay? And this obviously can be, you see, tau is just S hat over S, so you can rewrite it in terms also of S hat. An important point at leading order is that if, for example, this is S hat, this is the invariant mass of the TT bar pair, these two quantities are the same. Okay, so in a 2-to-2 process, leading order, the invariant mass of the final state and S are the same. So what is the shapes of these luminosities? Okay, we have these plots here that are also including some exotic content, let's say like this. But the main point that I want to show you is, this is, for example, for a 100 TV collider, you show what is the luminosity given an initial state, that is gluon-gluon or quark-quark or quark-antiquark, to produce an object of a given invariant mass. This can be a single particle with mass x, or a pair of particles at that given invariant mass. So the first important thing is that this luminosity starts at small value with incredibly large value and drop very quickly, okay? So the probability to produce something that is of the order, so that has an invariant mass that is the energy of the collider, is very, very suppressed. Second, you can see that already when you are at below 2 TeV, the ones that are dominant are the gluon-gluon one. Okay, so when you typically produce standard model process, a standard model process, if you think about it, the final state, you sum the mass of the particle, unless you have an incredibly large multiplicity, you have the invariant mass, the total mass that is below the 1 TeV. The gluon-gluon luminosity is very dominant. And in this slide, I also added, you see there is L photon, because all this discussion that we had here about the splittings, it's true also in QED. So it's true that this is enhanced in this collinear regime, but the same could be said if you have, instead of a gluon, here a photon. Obviously, it's an abelian theory, so the photon is not splitting into two photons. But you can have here a photon that is split into quark. Well, actually, not only quark, it can also split into lepton. So, in principle, you can also have a PDF of the photon at the proton collider, PDF of the lepton. They are incredibly suppressed, especially those of the lepton. And for practical prediction, you very rarely see the usage of lepton PDF for LHC, also 100 TeV physics. But in principle, is an object that can be there. So from a theoretical point of view, you also for the case of the lepton, therefore you can have a PDF of the lepton or the photon. Okay, so we saw that the luminosity are dropping incredibly fast. And if you want to write, for example, want to plot the cross-section of TT bar as a function, the partonic cross-section of TT bar, a function of square root of S hat, it has typically this, it has this shape. So it starts at 2m top, it gets a maximum, and then goes down like 1 over S. So the cross-section as a peak and goes down. The luminosity goes down. What is the effect of this? It's that, for example, if I look at the distribution at LHC, okay, I see that, for example, the transverse moment of the top starts to very high value, the cross-section for small pt, and drop. So we care only about the main panel here, not the other inset today. Start from very high value and then drop down. The invariant mass, the same, is having this kind of trend. So this is at 14 TeV. So what happens if you say I go from 14 to 100 TeV? One would expect, okay, I go to a more energetic collider, so I will have more energetic top pair. Well, no, because if you look at the distribution, they are practically the same, okay? So what is happening here is actually the normalization. So you here have 10 to the 2, 10 to the 2, and now you have 10 to the 4, 10 to the 4. So the spectrum in an hadron collider, if you include the energy, is not changing so much. So you are, for example, in this this TT bar production, you are mainly dominated by gluon. At LHC, 90% of TT bar production is gluon-gluon induced. At 100 TeV, if I'm not wrong, is like 97, 98%. So gluon are soft. If you increase the energy of the collider, what you are getting is more events, but not as a fraction of the total cross-section. You are not getting harder tops. It's true that the events are more. So obviously, if you put a cut, you say, I want invariant mass above 4 TeV, you will have much more events in a 100 TeV collider than in a 14 TeV collider. Okay, but this is another story. So it's not changing the shape of the distribution. Is really changing, especially the normalization. Okay, and you can see also that on the other hand, this can be a discovery collider. Why? Because first you have all these luminosities, okay, all these luminosities that so it can probe quark-quark interaction, gluon-gluon interaction. The quark-quark interaction are suppressed, but the luminosity still is very relevant. And if you have, for example, electroweak interacting processes, you don't start with a gluon, or at least at 3 level. And but you can see also that now you want to produce, instead of TT bar, like two, let's call it heavy top partner that have several TeV masses. It's possible. And it's possible especially in a different range. So the collider is 100 TeV, but it's allowing you to discover this the production of this particle, if they are present, not in a specific mass regime. Okay, so in general, over the spectrum, it's possible to produce this TT bar pair. Or, for example, we still have it there. You see, there is this peak that you see there. This could be done, for example, for the production of a Z prime. You have Q bar, Z prime, some L plus, L minus, something that is very heavy. So you move from LHC that was here to 200 TeV collider that is going up to here. You can see the resonance if there are enough events. You can see the resonance both if it's here or see if it's a bit displaced. It's not tuned, the collider, for the specific. So it's the collider allow you to discover different kind of particles and in a range of masses, not for a specific mass. Okay. Okay. Now let's go to E plus E minus. So this was the story of the of the proton-proton collider. You have question? I think most of you should know already these things, but if you have question, please ask. So if now I have an E plus E minus collider, I don't have a composite object. I don't have something that is formed of different particles. I have an elementary particle. Okay. So if I want to reuse this equation here, I mean, from a mathematical point of view, I can use it again. And instead of having the parton distribution function of a parton in the proton, I can have the parton distribution function of the electron in the electron, or the positron in the positron. Okay. So in the first approximation, if you want to do so the Parton distribution function of the electron in the electron, this would be delta 1 minus x, the delta function. So what is saying this? Well, the probability, in the first approximation, probability to get an electron that is carrying away a momentum, a fraction x of the momentum of the electron, probably this one is all related to the electron that is carrying away all the momentum. So if you do so, and you plug it inside here, what you get is that practically the cross-section is the Partonic cross-section, and you trivially get, again, that if you want to calculate the cross-section, you use simply the Partonic cross-section, okay? So this is the level 0, it's not the full story, but let's start from this, okay? So imagine now that you have FCC EE, okay, at an energy that is with the square root of S, that is a bit larger than 2 times the mass of the top. So which energy you want to have? Well, I don't remember if I just cancelled it, I think, but as I said before, the Partonic cross-section is something that has this shape. You build your collider where, if you want to probe TT-bar production, you try to have the energy that is picked here, okay? So this is sigma as a function of the energy of the collider, okay? Now, if I have this configuration and I plot the sigma in dm top top, that at leading order this is equal to no, okay, the m top top, okay, what do I have? I have just a line, right? So this is completely different from the proton-proton machine. Proton-proton machine, you have, for example, this is a 100 TV collision, starts from the threshold and drops down. So the typical energy that you probe for the hard process, the bulk of events are not at 100 TV. The bulk of events are at 2 times the mass of the top. If you are in a plus and minus machine, it's all picked at the energy of the collider. Okay? Completely different story. And also, as I said, the dependence on the cross-section, if you increase the energy of the collider and you want to study TT-bar production, you can increase as much as you want, but the cross-section is just dropping. So you're not getting more events, you're getting less events from this process. So imagine at E plus, E minus collider, the TT-bar production can happen with like a photon or Z propagators. If you want to start this process, you have to build the collider to stay here. You cannot say I make it more and more energetic so I study it better. While in a proton-proton collider, you get more and more events. So it's completely different because this cross-section, if I would show it for proton-proton collider, okay, so this is a function. Now I'm switching for a second to proton-proton collider. This would be like this, growing indefinitely, okay? The more energy you have, the more events you produce. And I think, oh wow, terrible view of this slide. Okay, but this is an example of, this is not TT-bar, it's actually TT-bar plus something else. So either one vector boson or 2 vector boson. This is the cross-section at PP collider as a function of the energy of the collider. What you see is that they all grow. Okay, if I do it at a plus and minus, instead it goes down. And especially you see that this is growing even more because it's the 4-top production that is completely dominated by gluon-gluon initial state. And so for the gluon and heavy objects, this increment of the cross-section with the energy of the collider is even higher. For the plus and minus, this is not the story. Okay. Well, actually, as I said, this was the 0 level picture. Okay, and this also I'm just drawing like another plot. This is now for a plus and minus. If you want to do it in PT, for example, of the top, I mean, it will be picked here at square root of s divided by 2, and it will go down like this. So actually, it's the opposite of what you saw in the proton-proton collider. If you look at TT bar, you are dominated as small pt. Again, here you have a spectrum. Here that is different. You can have hard top. You have many top that have the energy of the collider. So this is the zero level picture, as I said, because as much as this branching that is entering in the PDF is important in QCD, it is also for a plus and minus collider for the case of QED. So what we have neglected so far when we show this picture is the QED initial state radiation, okay? So if I have quark, gluon that has some properties enhanced collinearly and soft, similarly, you have it if you have a lepton emitting a photon, it's going another lepton. Okay? So this is very well derived, if you want to see it in a simple way, in the Peskin book, okay? In the chapter 17.5. But what is showing, you can see there, is that if you start with this idea that is the PDF of the lepton into lepton is equal to delta 1 minus x, taking into account this initial state radiation, it actually becomes another quantity. It becomes alpha over 2 pi log s over ml squared times 1 plus x squared 1 minus x 1 minus x. This is the plus prescription. I don't want to go into this detail today, but it's again a kind of distribution like the delta, and used to regularize the integral you have to do when you convolute this with the partonic cross section. But the important point to see here is the following: this log in a collider is giant, okay? Because here we have S, that is the energy of the collider squared, and in the denominator we have the mass of the lepton squared. So it's especially large in the plus and minus collider, because the mass of the electron is much smaller than the one of the muon, but is also relevant for the one of the muon. Okay? So it's large. These effects when are large? When the mass is small. So the smaller is the mass, the larger is the effect, so more for a plus and minus than muon collider. Or the energy is large, okay? But what is also important is that they are large when 1 minus x is small, okay? So initial state radiation are telling you that are especially important when you are very close to the energy of the collider, okay? So because this is telling you, okay, I assume like elementary particle that collide. If I put it inside this equation here and I use it as a PDF, how big I expect this effect? They are especially large if you are close to 1, because most of the photon that will be emitted will be collinear and soft. So they are changing your distribution from a delta to something that is mirrored like this. But if you go far away from the peak, they're not so important, okay? So you have this effect. On the other hand, as with the proton machine, if you have the emission of the gluon, you're not just changing the PDF of the quark. You can also consider gluon-gluon initiated processes. The same is here. If you start to take into account this effect, you can have a photon PDF. Okay? No, you can have a photon PDF, and for example, having this kind of process, E plus, E minus, that emit a photon, and this is producing 2 TT bar pair. Okay? Because now, if I'm taking into account initial state radiation for modeling the distribution of the electron in the electron, and notice that we are using the same mathematical language for 2 different cases, and the big difference is also that when we see the probability of finding an electron in the electron, we are using the same language of the PDF of the PP collision, but in fact we are just the electron is just only one. It's just that we are taking into account the collinear emission. Okay, so we are again moving, depending on a scale, this multiple emission of photons that can branch again to electron into something that is universal, that is related to the beam itself or the electron, and some other part that is related to the process. But if you do that, it means that you can also have the probability of a photon into the electron. And if you write, if you look at this probability of the photon into the electron, this is equal to alpha over 2 pi, again the log s over m squared, but then multiplied by 1 plus 1 minus x squared over x. I mean, you see, if you just take this equation and you substitute x with 1 minus x, you get this other one. Because in one case, you're looking the fraction of the electron in the electron, the other one, the fraction of the photon in the electron, they have to sum to the same. And this is different just for one aspect, because again, it's very large if the mass is small, and very large if the collider energy is large. But it's very large if x is small, okay? It's like the gluon now. So the photon emitted from the electron tends to be soft, okay? So now we had this picture here. In reality, the picture is a bit different. Okay, so it's something that is not a peak, is something that is going down. Let's say it's going to super small value, and then there is a very small bump here, close to 2 times m top. So this, you can imagine, is like the process. So this effect that you see here is the one that is coming from the diagram that we have here. And this being, this shape here is the one that is coming from this other process, okay? And what is the problem here is that you have a large log also for the photon, but as I said, these photons are picked, okay, for small x. Okay, so now, if I've built a collider, I want to use to study TT bar production, you will set it at an energy that is the one that I showed there. Okay, the energy of the collider will be of the order of 2 times m top. Okay, bit larger. The peak of the cross section is a bit above it. Okay. The problem then is that tau will be of the order 1, just a bit smaller than 1, okay? Now, if tau has to be just a bit smaller than 1, and tau is actually x1 over x1 times x2, it means that x1 and x2, they have to be also close to 1. But if they have to be close to 1, this quantity is not large. And this is the reason why I draw the picture in this way. It's true. If you have an E plus E minus collider, you can have processes that are photon-induced TT bar production. But you know, if you look at the distribution here in X, it's very difficult so impossible to get to this effect, because you can never have the X that is small, given the fact that tau is also has to be close to 1. Obviously, as I said at the beginning, I'm referring to a plus and minus collider, let's say at low energy. If you start to look at plus and minus collider, like you have in mind the click or ILC, you go to TV region, the story is changing, okay? But before going to that, I want to show you another important point, that up to now, what we have written here kind of cheated, because it's not really the PDF, okay? PDF is something that has resummed inside of it the multiple emission. This is what is called, for example, EVA, so effective vector boson approximation, in which you are taking one single emission, okay? If you want to take into account multiple emission, you are going back really to the PDF language, like in the case of proton-proton collider, and you have to resum all this emission. And why you think why is important to resum? Well, because these effects, although they have in front alpha that is 1/100, they have this log that is giant, and the x can be as close as you want to 1. So these effects can be much larger than order 1. Okay, so one single emission in some points can give you an effect that is order 1. So if one emission is going to order 1, it means that having multiple emission is more important than have a single emission. So you have to go back again to the Altarelli-Parisi equation. But what is the difference? Is that you don't need the data. I mean, the difference with the proton-proton collider is that you use this PDF language because you have to resum the emission of gluon and quark collinear, but also because you need a framework to model the proton that you are not able to calculate from a first principle. So you combine the two effects. Here, you can solve the Altarelli-Parisi equation, actually, and if you do that, what you get is the following. So you can solve the Altarelli-Parisi equation that are similar to the one that I showed before for the QED, setting the scale mu f equal to the mass of the electron and the PDF of the lepton inside the lepton x at the scale m lepton equal delta 1 minus x. And you get, this is the leading log, the most simple version, is you get something that is like an exponential. For gamma e 1 plus beta 1 minus beta times 1 minus x at the beta minus 1 with beta equal alpha over pi log of mu f over me squared. So this is a quantity that, for example, if you expand in alpha and you go in the limit of x that is equal to 1, you will see that the first expansion in alpha will be, you can try to do it with Mathematica, it's very simple. You get that the limit x equal 1 is equal to the quantity that we see here, but it's very different the expansion from the value. So you cannot just take one single emission, okay? I mean, this is super important for like precision physics at the plus and minus machine. You cannot do this only in this leading, this is called the leading log approximation. You have to go to next to leading log, and what you get are a PDF like this one, okay? So, for example, this is the PDF of the electron in the electron. It's picked here, it's going down for very, Z is like X when I was saying, it's going down, and then it's going up again. Why? Because when you go to very small x, you have the photon instead that is growing. But if the photon is growing, it means that also in principle the photon can split into an electron and a positron. So you get again a kick here from the electron in the electron and a small x. But then you get also a positron. So actually there is a PDF of the positron in the electron. It's very suppressed, but is important. Okay, this is super important for I plus, I minus. Okay, but you can now already imagine what we are going now. We are going to the Muon collider. Okay, the Muon collider has an important difference with this I plus, I minus case that I showed you. Okay, Muon collider, as we said, has an energy that is much larger than the one of this I plus, I minus collider that we consider. So S is equal either 3TV squared, the two cases that we are considering, or 10TV squared. Okay. So 2m top is of the order of 340 GeV. So tau, so the minimal tau that you can consider is 340 over 340 squared over S over S. So this is going to 10 to the minus 2 or 10 to the minus 3 level for the 3TV and the 10TV. So you see that the argument that I said before, no, we cannot have so much photons because the peak will be small, because tau has to be close to 1 and the x have also to be close to 1, it's not true anymore, because you can produce two tops with a tau that is very small. So also the x can be very small. So also the photon is important. So in fact, we will see really plots, but having it like a sketch, if you look at the distribution of d sigma in d mtt, in a Muon collider, it's something like this. Okay. So what it means? It means that you have two regions. The region 1, okay, which you are dominated by process like this one. Mu plus, mu minus, mu plus, mu minus, that emit a photon, but since the photon is emitted very collinearly to the muon, to describe it, instead of using the full process here, I can use the PDF of the photon in the muon and write the photon-photon to TT bar production. Or the region here in which I'm dominated by mu plus, mu minus to TT bar. So it's like, it's having a spectrum that if you look at it, is a combination of the one that we saw for the proton-proton machine on the left, and the one that we saw for like low energy plus and minus machine. And there's not obviously a clear cut. Then they are merging smoothly. Okay, so there is also the valley here in the middle. So this is telling you that the shapes, the distribution will be dominated by two different regimes. And also all the challenges that you had in precision physics in proton-proton machine, you have it also in here, and similarly in a plus and minus machine. When I said the hadronization of the leptons, I precisely meant this point, that you start to have distributions. They are the one that you typically have at proton-proton collider, not at the plus and minus collider. Okay, but actually the situation is even even more complicated. Okay, because so that this energy 3 or 10 TeV are much larger than the mass of the moon. But they are also much larger than the mass of the Z, the mass of the W, the mass of the X. Okay. So all this story of the PDF, the collinear enhancement, and the fact that you can describe a process rather than using these diagrams directly with the PDF of the photon in the moon. So the probability of getting a photon in the moon and then just the process here. They derive from one fact that the mass of the fermion over square root of S is practically going to 0, and the log of square root of S over mass of the fermion is going to infinity, much slowly than the power. But I mean, if you increase the energy, you have this situation. So you can actually forget in first approximation the power correction, take into account only the logs, and since the logs are so large, you need also to resum it. Now, if now you put inside here, instead of MF, you put MW, okay? This is of the order 0.01 at 10 TeV. Okay. So the question you can ask yourself is, can we do the same with the electroweak vector boson? With the gauge? Because this is a question that was not present before, because the energy of the collision, for example, in a E plus E minus machine, has always been of the order of this electroweak vector boson. So this was order 1, not order 1%. So the similarly are the equivalent log of this quantity very large. So what I'm going to introduce here, and then we will see more details next time, is the fact that as much as you can start from the EVA that you have here, so you can start to generalize this EVA, effective vector boson approximation, to what is called electroweak boson approximation. So we have F gamma, and this is the EVA, okay? And this comes from the QED interaction, okay? And the Feynman rules, here I write a mu here for the photon, F is minus IE F gamma mu. But then you can have Madonna. UIG cos theta W gamma GVF 5 G V equal 1. And also so this EVA, so effective vector boson approximation, is for QED. For the QED, you have these Feynman rules. Okay. In the case of the electroweak boson, you have W that is interacting only with the left-handed components of the fermions, and it has a coupling that is this G, okay, where G is actually equal to E divided by sen theta W. And then you have also the Z that has these other couplings and different interaction with the vector-like and axion-like part of the interaction. Okay, so you can generalize the expression that you have here to the case of a vector boson, keeping another point in mind that in this collinear approximation, while in the case of a photon, the emission of the photon was regulated by the mass of the fermion, because the photon was massless and the regulator was the mass of the fermion. Actually, the one that is regularizing here the collinear enhancement is the mass of the Z boson or the W boson. So instead of having log of S over ME squared, you will get things like log of S over MV squared. Okay? So these log are obviously much smaller, but also you have to take into account that instead of having in front this alpha, you will have some that are induced by the interaction that is the E. You will have also here E over sen theta W, so you will have the weak interaction that is stronger than the QED1. So log are smaller, but the interaction itself is larger, plus S is larger than it was in a plastic minus collider. So there are a lot of difference, but they become important at the end, this collinear emission also for the W and the Z. And also, as you can see, they have a different chiral structure, so they're interacting differently with the left-handed and right-handed. Okay, so doing so, you can get actually what is called, as we said, electroweak effective weak boson approximation. Remember that all this discussion, as I said before, relies on the fact that the mw over square root of s is small. We will come back to this point because there's more to discuss on this expansion that is related to the energy of the collider. But I will come back today or tomorrow because we will inspect in a more critical way this assumption, but this is the assumption that we are having now. So now, doing so, you can have some, we said, electroweak effective weak boson of approximation. So, for example, you have a probability to have a right-handed vector boson into left-handed lepton x f is equal to g tilde over tilde squared over 4 pi squared gl squared 1 minus x squared over 2x log f over mv squared. Then you have similarly v minus into fl, so left-handed vector boson, left-handed fermion, x over f equal g tilde squared over 4 pi gl squared 1 over 2x log f squared over mv squared, where this g tilde it changes depending of the vector boson that you consider. So g tilde is equal g over cos theta for the z and g over square root of 2 for the w. And then you have this gl that are defined as gv minus ga, and gr that is defined as gv plus ga. So what is the important point to see here? Again, there is 1 over x. So this is telling you the PDA, the EWA of the Z boson or the W boson is picked as small x. It's like the photon, okay? You produce them exactly that are carrying away a small fraction of the muon moment. Okay. Then also you have different interaction for different helicity. So this is already telling you that if you would build a polarized muon collider, there will be a very different contribution from the from the effect on vector boson collision. And also, last but not least, you have also other contributions that are coming from the longitudinal polarization, because obviously now it's not a photon, it's a massive vector boson, so you can also have longitudinally polarized vector. F that is not carrying actually the log in this case. So point that I now want to do that I think is really important is that when we introduce the photon PDF, okay, so the EVA, okay, so you start actually, as I said, from this process, photon t bar, mu, and you go to the description of it like f of gamma into the muon, with this one that is the EVA, and you use this one, okay? Similarly here, what I'm doing is the following. I'm taking, for example, another process that is muon, neutrino, W, muon, neutrino, W, TT bar, and I say it's so important the emission of W that are collinear, instead of describing like this, I use the EWA, so the F, probability of the W in the muon, probability of the W in the muon, and I multiply it for the process W into TT bar. Okay? So it's clear that in both cases, if I move from this to this one, or from this to this one, I'm limiting myself to the collinear case of the muon, or this muon to this muon, or to this neutrino to this muon, and I'm also neglecting other diagrams, okay? Because if you look at this final state, like muon to muon TT bar, but you could have the same process in which you have TT bar, in which you have a Z or a photon, and is emitted other two muon. So in the amplitude for this process, there is this diagram as much as this diagram, and there's no way I get this diagram using the EVA with this other diagram. Okay. However, what was the reasoning? Was that the log here of emitting a photon are so large, okay, that is very dominant, this contribution with respect to these other diagrams. And these logs are so large that not only this is dominant, but I have also to resum the log, okay? And actually, it's more important for some distribution that taking this log, resum them using only this diagram than taking all these effects. That are also effects that we said are of the order m over square root of s correction. Now, in this case, the situation is a bit different because it's true, like again, I'm approximating, so I'm neglecting also some diagrams here because, you know, if this was the Z, I can put nu, and again, this diagrams is entering as part of the diagrams for this process, okay? But also I'm forgetting power correction, that, you know, all this discussion started to saying like, okay, power correction are of the order of 0.01 because this is equal to mw over the square root of s of the collider. Actually, when you calculate the amplitude, the energy that is entering here, so the hard process, is not the energy of the collider, is the energy of the hard process. And we just showed that the vector bosons are picked as small x, okay? So this means that the partonic is much smaller than s. And so when you do this argument, it's partially true. Because if you are doing an expansion close to the threshold, I'm going the extreme direction. If you produce two tops, this will be of 340 over, of mw over 340. Okay. Now we're not speaking anymore about 1%. We're speaking about order 25%. Okay. So it's a different story. But the main point is that the PDF of the photon is necessary. Necessary at the plus and minus, and is necessary at the mu plus minus collider. The EVA, EWA, is an approximation of the full calculation. An approximation that is super useful because, as you can imagine, calculating 2 to 4 processes is more complex than calculate 2 to 2 processes. If you've ever done a calculation by hand, you know it. And if you go to high order correction, it's even worse. So definitely, this is helping in simplifying the calculation, is helping also to understand the nature of the collider because it gives you a clear picture on the fact that it's a vector boson collider. This is still true. This is an effect that is very dominant. The fact that using the EWA is better than doing the 2-to-4 computation is clearly not true. The question is still open now in the community, I have to say. I mean, I have my opinion, but I have to present it as it is because it's something that is still discussed now, is okay. Now, in the QED, we go from the 2-to-4 to the PDF. So we go to the collinear approximation and then we resum them. Should we do the same also in the for the electroweak boson at the muon collider? So should we go in the collinear approximation of the EVA, then resum them, have electroweak PDF and model the processes with the electroweak PDF that are resumming these logs? The fact that this approach is superior to the fact of doing matrix element calculation is something that is really discussed nowadays also in the theory community. But people have done the electroweak PDF. This is since a few years. And this is what you see, for example, for the electroweak PDF. These are the electroweak PDF of the muon. They're taking into account this collinear enhancement, and they're resumming them. And what you see is even more now what I discussed as before, the dronization of the lepton. So you are having as the lepton, as the proton-proton collider. If you go in this picture, you have partonic initiated processes that are mostly peaked as small x, so they are going to induce dynamics that is similar to the one of the proton-proton collider. The only one that are peaked on the right is the muon in the muon and the neutrino in the muon that is coming from the muon to W neutrino splitting. If the W is soft, the neutrino will be hard, suppressed, but will be hard. And then you see all the other are much more enhanced at small x. And you see that they're appearing also gluon and quark, because as a proton-proton collider, I said, okay, we speak about gluon splittings, but you can also have QED splittings. Similarly, in a muon collider, you can have the emission of a Z, the Z then is splitting into two quarks, and then the quark is emitting a gluon. And when you go to small x, you can even have very small x, even the gluon in the muon, okay? And if you look at the luminosity, you see that on the right hand, you are dominated by the muon luminosities, and this was exactly the picture that I said that looks like an E plus E minus collider. And on the right, you have the photon-photon collider, photon-photon collider, yes, with photon-photon luminosity, but you have many other luminosities that are contributing, okay? So these are the kind of picture that you see. This is the one that I drew before, in which there's not only muon-muon to muon-muon, but there is also photon-photon and all the contribution that you see here. And so, for example, you see that the more you go with the energy, the more the collider starts to look like a proton-proton collider, because here I'm plotting not only for TT bar, but for different final states, the cross-section as a function of the energy of the collider. And so the solid line is the prediction, but there is dotted the one that is from direct production, and dashed the vector boson fusion induced one, so the one from vector boson collision. You see there is always a point in the energy in which the vector boson fusion start to dominate and is leading to the bulk of the cross-section. And this depends from the process itself. But this has been studied for several processes, and here in the few slides that I'm showing before stopping, because I think it's 11, right? Roberto, I have to stop now, right? Yeah. These are just several processes, final states, like for example, TT bar Z, TT bar X, here with other, in which we plot, they plotted here the cross-section induced by the hard process that is mu plus mu minus that go into the final state from the one that is induced from WW collision, W emitted from the muon. And you see that the solid are the the fusion, WW fusion, there is always a point that is crossing the other and leading to the largest results. And similar here for other processes. So this is really like showing that the higher you go into the energy, the more the peak that we have shown on the left in the distribution of the invariant mass, also that that is typical from the proton-proton collider, is becoming more and more dominant. And you are dominated when you study your process by scattering of vector boson that are carrying a small fraction of the momenta. And I think that for today it's okay if I finish here also, not only for the time.
There is a question time this afternoon. You are invited. I don't know if you knew, but yeah. You know you have to be in the afternoon.
I don't remember what time, but I remember
Okay,
there was a
okay.
moment I have to be here.
So I don't remember if I told you.
Yeah.
So very nice talk, many thanks. So at some point you mentioned that yes, the muon collider combine, let's say, a discovery machine and precision and lepton and proton with a valley. Is it an advantage to have this valley in the same machine? I mean, can you measure things that you could not measure in some colliders?
The valley for sure is a region that it would give a low background for possible new production of new states. This is the clear method. The problem is that the valley, since it's low events, low number of events in a standard model, is also the one that is more subject also to possible high order effects. Because, for example, there in the valley, the emission of an additional, for example, Z or W is giving a large contribution, much more than in another point. So actually, it's a point that it's true. You need to have you have a low background from the standard model, so more sensitivity, let's say, to events from BSM dynamics. But you need to have, I think, it could be more difficult to have under control the uncertainty from the standard model itself.
There was another hand.
Yeah.
So you said that there is debate between what is best between using this electroweak PDF approximation and the exact matrix element computation. So what do you mean exactly by matrix element computation in this case?
I mean, I will discuss this also in more detail if I get to the point at the end of the next lecture, but the fact is when you use the EWA or the PDF, what you are doing is simplifying your calculation. So the EWA, let's say, you are simplifying your calculation. You are saying, I have, for example, for the case of the WW to TT bar, you say, I want to calculate mu to TT bar neutrino, okay? But I don't care about tagging the neutrino. I'm just inclusive in the radiation of the neutrino. What I'm interested in is looking at the TT bar. So I realized that if I do this computation, a large contribution comes from the region in which the muon is emitting the neutrino and W collinear to each other. Okay, so then if this is the case, okay, I can simplify my calculation looking only at the process that I have here, that is not anymore mu to neutrino TT bar, only this one here, and convolve it with the probability of having the W in the muon. Okay, so when you do this, you clearly see that you are, by definition, focusing on vector boson fusion diagram, because you're selecting something that starts with W boson fusion. But inside all the possible diagrams that you have here, There are others. So for example, if you have TT bar plus Z with a Z that emit a pair of neutrinos, is giving exactly the same final state. Okay. Then clearly you can set some cuts to enhance this, but the point is this is an approximation of the full calculation that is that one. Okay. The same is true for the QED part. But in the QED part, the logs are so large that this approximation that is very good, and the logs are so large, not only are the dominant one, but that perturbatively, they are not enough. You have to take into account all the possible other emissions, and you have to resum them. Okay? So actually, simplifying using the PDF in this case, you have more advantage in the description than taking into account all the full matrix element. Here instead the situation is different. Because they are not so large, okay? And this is exactly what I'm also trying to show tomorrow. And this is precisely one of the challenges that we have at this moment for the discussion, because obviously matrix elements are not resumming these logs, but appears to be bad at least. This again, I want to present it in a fair way. This is not something like the truth. I mean, in general, if someone is telling that something is the truth, there is a problem. But this is something that is really studied in this moment. There are clearly people that have also different opinion than me, but it is appearing more and more that it's very different, the situation from the electroweak vector boson and the photon. And although it's very appealing, this picture, it has to kept in mind as a picture that helps you to understand the physics, but is not leading you to the most precise results, at least it seems to me. And so if you want to have prediction in the standard model that are accurate, for the case of the vector boson fusion process, it seems that it's more important to take into account all the diagrams. All the diagrams 2 to 4 is much more complex. So this is telling you again, if you want to have the precision, you pay a price.
Okay, thank you.
Don't forget you can also run the sheet, but yeah, please.
Maybe a naive question, but you say that when you use PDFs, you neglect those diagrams when you attach a pair to the initial state. Are gauge invariants separately? Or just at leading logarithmic level?
No, the point is so when you take an amplitude, so what can happen sometimes is that in an amplitude you have diagrams that you cannot separate exactly because of the gauge invariance, okay? But if you are interested only in the collinearly enhanced contribution, those are separable, okay? So since you are interested in the collinear enhanced contribution, there is more freedom in separating the diagrams. Okay, if you want to take into account also the power correction, no, you're perfectly right. It is also a problem. Is a part of the problem that you can you have less freedom in separating the different contribution if you want to be accurate not only at the collinear level but at the full level. Okay.
And that's your situation because
but not. I mean, the typical. I mean, the typical.
The pole on the Z propagator cannot be mixed to the vector boson fusion topology.
No, but I was referring to something more general. That is, for example, if you take, for example, process like E neutrino W. neutrino, and then you do you look at the emission, for example, you emit a photon, okay? So you add a photon. The photon could be attached here, could be attached to the W, could be attached here. Now, if you say, I just consider the one that are emitted from the E and not from the W, okay, you cannot do it. It's not gauge invariant. Now, if instead you say, I want to look at the poles, okay, I want to look at the collinearly enhanced pole, the poles have a different gauge structure than the full matrix. So since the collinear limits have a different gauge structure, this can be gauge invariant, okay, just the poles. So since the poles can be separated in a gauge invariant way, then this is what allow me to separate the diagrams from the other, because you are just selecting the collinear enhanced component. If you want to have the full, no. This is a general structure. Then there is also the things that you also say, that you are probing also different kinematics. But there are something that is more theoretical, and other also to the distribution.
Any more questions?
I have a stupid one, so you can take my degree away at this point. No, I'm a bit confused by the fact that you said at the beginning that going to 100 TV from LHC is just an overall rescaling of the TT bar differential cross section. I mean, this I would understand if it was only a single log, but in general, I'm a bit confused.
For the...
No, you showed the TT bar cross section.
Proton.
Yeah, proton. And you said it's only an overall rescaling of the
no, there is a. So, these are. Let me see. You see, these are distribution. This is like the PT of the top on the left. So let's take the invariant mass in the middle. This is the distribution of the invariant mass at LHC. This is the distribution of invariant mass at FCC. Okay. So mostly the effect is putting up the distribution. So you are shifting the distribution up in number of events. Okay. Instead, if it was ID plus E minus collider, the invariant mass distribution would be picked before at the energy, and then would be.
No,
so
this is clear.
Zero.
This we understand.
Level 0.
This is clear, but the fact that it's really just a rescaling and doesn't really change the shape in any way, I agree that it has to be picked at low PT or low masses. This is clear.
No, there is a bit of a changing in the shape, and this you can see it from this other plot here, because this is the ratio of the PDF luminosity at 100 TV over 14 TV, okay, for a given invariant for a given final state mass, okay. So you see that the higher you go to the final state invariant mass, the higher is the ratio between the 100 TV luminosity and the LHC. So in fact, it's true. What you say is that there is also an effect that is tilting up the tail. This is what you see here. But I was focusing more in the general pattern. So the message also that you get here is that if you, for example, take the production of an object that is heavy, the benefit that you get in increasing the energy of the collider is higher, the higher is the mass of the object itself, especially for the gluon. Because you see this plot here are for the gluon luminosity, quark gluon, quark antiquark, and quark quark. The trend is the same, but it is especially for the gluon. And it's the same reason why, for example, here you have also like for top that is growing a lot because it's completely induced by the gluon, is more massive, so the increment. So this was what I mentioned before was the first order level. Then there are also these other effects that you mentioned.
I don't see puzzle faces. So we can thank Davide once more.